Okay, in this lecture, we're going to finish up the theoretical part of the discussion about matrices. We'll talk a little bit about solutions of linear systems, talk about existence and uniqueness. This lecture is possibly optional if you don't have a lot of time. We're just going to summarize some of the things that we discussed in the previous section and put a little more mathematical formalism around it. So, there is a fundamental theorem in linear systems that basically states that if we have a linear system of m equations and n unknowns, so our variables run from x subscript 1 to subscript n, this is consistent or it has solutions if and only if the coefficient matrix and the augmented matrix have the same rank. So here's our coefficient matrix symbolism, here's our augmented matrix symbolism. So the existence part of the theorem, we have basically our m by n matrix and our augmented matrix. And so the uniqueness part says that this has only one solution, and it has that solution if and only if the matrix and the augmented matrix have a common rank r, and that rank r is equal to n. So in other words, once we find the reduced echelon form, we should have rows of zeros and then a square matrix above that. So the rank r has to equal n, the number of unknowns. We have infinitely many solutions if the rank is less than n, so we would have an unspecified variable that we would have to parameterize. All the solutions are obtained by determining the suitable unknowns. So you would have to determine if you have rank r, you would have to solve for r unknowns. And then you would have to assign arbitrary values to your remaining unknowns. If the solutions do exist, they can all be obtained by Gaussian elimination. In fact, Gaussian elimination is one way to find out if you have a solution, because it will be a self-consistent method. Also recall that if all of the b sub j's, all of the solution side of the equation, the right-hand side of the equation, are zero, that's referred to as a homogeneous linear system. And if they're not all zero, even if one is not zero, then it's referred to as a non-homogeneous system. So here's an example of what a homogeneous linear system looks like. Notice all of our b's are zero. And this will always have the trivial solution where all of your x's are equal to zero. Now, non-trivial solutions will exist if and only if the rank of a is less than n. If the rank of a is equal to r, which is less than n, then all of these solutions, together with x equals 0, will form a vector space of dimension n minus r called the solution space. In particular, let's look at an example. If we have a vector x1 and a vector x2 and they're solution vectors, then a linear combination of those two with any scalar is also a solution vector. It's important to note that this does not hold for non-homogeneous systems, because non-homogeneous systems, remember, will have a unique solution. Also, the term solution space is only used for homogeneous systems. The solution space is also called the null space because ax equals 0 for every x in the solution space. And its dimension is called the nullity of A, and we can recall that we previously in a definition learned that our number of unknowns n, the rank of A plus the nullity of A will have to sum to n, where n is the number of unknowns. And furthermore, by the definition of rank, we have that the rank of A has got to be less than or equal to m, which, if you recall, is the number of rows. So if m is less than n, so the number of rows is less than the number of columns, then the rank is less than n. If we have fewer equations than unknowns, we will always have non-trivial solutions. So if a homogeneous linear system is consistent, then all of its solutions can be obtained from the following. X is equal to x sub 0 plus x sub h. Where x sub 0 is a fixed solution, and x sub h runs through all the possible solutions of the corresponding homogeneous system. So that concludes the section of just sort of summing up some of the theorems that we've discussed. We've done some definitions. Just wanted to do a little bit of a summary so that you would have some perspective on that. The next lecture will cover matrix inversion.